Hi, my name is Jonathan Schneider, and welcome to my session today on how to fix your technical debt dilemma. I'm really excited to introduce you to a technology called OpenRewrite, which is a mass automated refactoring engine that allows you to write small programs to rewrite other parts of your programs to do things like major framework updates, patch CVEs, fix stylistic issues, and so forth. But first, a little bit of background on how we got to this point, why such a thing is even desirable or necessary. And I think I'd start with saying that the software industrial revolution has arrived. We have an explosion of custom applications and therefore source code, and we assemble them quicker than ever before. At one company we work with, today there are about 70 engineers, and if you rewind back to 2014, there were 70 engineers then too. The difference is in 2014 they had 40 source code repositories. Today they have over 900. So with roughly the same team size, there's 25 times the amount of software under management. And this has happened because modern application development has actually changed. We assemble software more than we build it. It's 80% open source and third-party components, and we stitch that together with 20% kind of glue code that assembles some customer experience. It means that we can build applications and build new business value and customer experiences very quickly. But it leaves us with a large application surface area, a large volume of code relative to the number of developers that we have. This has had other impacts, of course. The attack surface area of our businesses has expanded, but I think more importantly, the maintenance surface area of our businesses has expanded. And so right now, developers spend roughly 30% of their time doing tedious migration type tasks. So adjusting to changing APIs that, of course we don't control these open source frameworks and third-party dependencies, so they evolve at their own pace and we're kind of left just trying to keep up. And this work isn't fun. So it's often very mechanical. It can be described algorithmically, just complex enough that it eludes basic search and replace type technologies, but easy enough that it winds up still feeling like a very menial task. So how do you maintain applications more effectively? I say that OpenRewrite is a form of engineering that we'll call migration engineering. For anybody that's worked on a central team, like a build tools team or a platform team or an application framework team, I think you know what I mean. It's when you try to make changes to the core technology, you're left trying to promulgate that change across every product in the organization. The whole technology here started for me when I was working at Netflix on the engineering tools team in late 2015. I was working on a team of 2 or 3 build tools engineers at any given time, and we were trying to promote new patterns and fixed deprecations in just the build part of the application logic. But we had 700 engineers, product engineers that we were working with. So it becomes a question of how do we scale our knowledge to the rest of the organization. At some of the larger organizations we work with today, languages and frameworks team may have the management of an internal application framework that has hundreds, thousands, even tens of thousands of applications built on top of them. So what we need is an approach to automated software refactoring to keep up with API changes, fix vulnerabilities, and improve code quality in a more systemic way. To just list a few kinds of use cases to give you an idea of the kinds of transformations that we're capable of doing. OpenRewrite is used to do big lifts like Java 8 to 11 and to 17, to do framework updates like Spring Boot 1 to 2 and then later 2 to 3, to fix patterns in code like appropriately using or not using string concatenation in logging statements. It can be used to go hunt down and remediate security patterns, like we all were in the Java ecosystem confronted with a significant vulnerability called Log4Shell earlier this year. And it was kind of up to our central teams, or actually all of our product teams, to go track down all the potential exposures and fix them by hand. And then lastly, to deal with API changes, maybe internal API changes that we're trying to make to improve our internal frameworks for whatever reason. OpenRewrite is based on abstract syntax tree manipulation. So it's not source code manipulation. It's not just trying to fiddle with the actual bits of text. That text of the code is transformed into an abstract syntax tree. And for languages, like more complex languages, OpenRewrite leverages the language's compiler to take that abstract syntax tree and type attribute it. So for example, when you look at a method invocation, the type attribution information would contain the information about where that method was declared, what its formal argument types are, maybe its declaring type if it has super interfaces and other methods on it. All of that information would be attached to the syntactic element of a method invocation on the tree. And then lastly, OpenRewrite's AST is also imbued with the original formatting of the code. And this is really important because if we're going to make a change and suggest we're going to do abstract syntax tree manipulation, we're transforming it from text into tree, and then we need to print it back out to text to generate a diff that will become the basis of the change. It's really important for that diff to be as minimally invasive as possible. We want that diff to look like a developer on the project made the change. So let's flip over for a moment and see an example of a particular transformation, so you get a sense of the kinds of stylistic preserving things that this really gives us. This is a diff, a PR generated from an OpenRewrite recipe that's designed to move an application from JUnit 4 to 5. So in the Java ecosystem, JUnit is a common unit testing framework. There was a major version update recently, and that changed things that look fairly trivial, like it changed import statements. What used to be org JUnit before is now org JUnit Jupyter API before each. We had to change every annotation from before to before each. We had to drop some annotations which are no longer relevant, like this one. But some of the changes are much more structural. You used to be able to define an exception on the test annotation, but in JUnit 5 you have to use a method called assert throws, and you put the exception as the first argument to that method, and then the rest of the method body that's guarded by that exception goes into a lambda. And so these are the sort of changes that, if I was to do this by hand, it would be very mechanical in my mind. But it's hard to imagine how to do like a grep sort of regular expression replacement here to affect this change. The things that are a bit, I think, more hidden about this are things like import manipulation. If I'm going to remove these 3 imports in the old assert package and add these 4 in the assertions package, should I be instead using a wildcard import here? Does this project use wildcard imports? If so, how many types inside of a package need to be part of the import set in order for me to use a wildcard? Is it 3? Is it 5? So these are the sort of things, these stylistic characteristics of a project that Rewrite will backwards derive from the formatting of the project itself, so that when it does lower level things like import manipulation, that it looks idiomatically consistent in the context of this project. In this case, this project didn't use star folding. The org JUnit and the block of imports existed at the end, and so this change looks right for this project. For the assert throws block we just looked at, I can tell that this project uses tabs. So the new block that we're going to insert here uses tabs as well. The same recipe that makes this change applied to a different project would craft changes that look different. They would look consistent in the context of each project. OpenRewrite itself is an Apache 2 licensed refactoring engine. So the parsers that produce type attributed ASTs and all the recipes that my team and I developed, we Apache licensed them all. The basic experience of getting started with OpenRewrite looks something like this. You can go to docs.openrewrite.org and see, but it would be applying a build tool plugin. So the basic experience is integrated at the build, where you would be applying a build tool plugin, configuring the recipes that you want to run, and then ultimately running a build tool task like rewrite run that would make all the changes, suggested changes on disk, and then it's up to the developer to accept the change or make further modifications. So it's just like giving the developer the superpower that they could run a recipe and some migration is achieved or some stylistic consistency thing is achieved, and that's just very quick. Alongside OpenRewrite, there's also a public service that we run called Moderne, which runs the same recipes, so these same Apache license recipes, on hundreds of millions of lines of open source code. And so to give you a sense of the breadth of what the framework can do, we're going to hop over to Moderne, and just remember that any recipe we run there, you could also run with a build tool plugin on an individual repository. I just think it's more interesting for you to see it as it applies to many, many projects simultaneously. So this is the Moderne service that's being run, again, for hundreds of millions of lines of open source code, public.moderne.io. And you see a recipe catalog. These are all the OpenRewrite recipes, and they're broken down into different categories, like Java in this case. Let's look at one. We'll actually start with something like search, which we actually view search as a special case of transformation. We're going to take the abstract syntax tree and add what we call a marker, which is just a little arrow, just an indicator that at a certain place in the AST we found something that we're looking for. And I'll show you how that's rendered here. So let's start with looking for a method called java-lang system.getProperty. And this is we're going to start with this search to just see how prevalent this particular method is. And then do a change on it afterwards. So this is a recipe, an OpenRewrite recipe called OpenRewrite Java Search Find Methods. This one in particular has options. So there's inputs to this recipe, the fully qualified receiver name and method name and argument types. If we run this, we're going to run this on a set of, say, 64 repositories initially. And note it runs very quickly, and I'll explain more about why that is in a little bit. But if we click into any one of these repositories, you'll see that we've accurately identified this method called system.getProperty. We talked about the abstract syntax tree having type attribution information earlier, and the type attribution information is what allows us to 100% accurately identify calls to system.getProperty. We're not looking for just methods called getProperty, the syntax element, because those may come from different receiver types. We're looking for actual calls to this fully qualified target. And if we're going to build accurate migrations that don't have false positives, this kind of thing is really key. Change method target to static. That's the one that I wanted to do. System getProperty. And we change this to IO Moderne system properties, for example. This one's interesting because this involves changing both that static target that you saw on the front, the system to system properties, but it also involves import manipulation. So if we look at one of the results here, you'll note that I have to add an import. This would definitely elude what a regular expression could do. It's two different pieces of the code entirely that I have to modify. So this is an example of one of these sorts of changes. you can see with this change method target to static that recipes build on lower building blocks. So this is a rule-based system where recipes become increasingly sophisticated by building on lower building blocks. If we look at a more complex recipe, like the JUnit 4 to 5 example from earlier, you can see how recipes can chain other recipes to do very complex things. So this is JUnit Jupyter from JUnit 4. And it involves other recipes, like using the WireMock extension. It involves some base building blocks, like there's a base building block for reordering method arguments, for changing types. And the change type would, of course, change both the occurrence of that type in the code, but also do import manipulation as necessary. So it, in turn, chains to others, base building block recipes. And you've got a whole list of other sort of recipes, other, base building block recipes. This then becomes a building block itself, JUnit Jupyter from JUnit 4, that can be used by higher order recipes. So for example, to move from, I think it was Spring Boot 2.3 to 2.4, you also had to go from JUnit 4 to 5. These are the kinds of things that we want to see, is the packaging of recipes that do more and more complex things. Ultimately, one of the changes I would like to see in the software industry is that framework authors, the ones that make the API changes, become responsible for providing recipes that fix the things that they're changing. It's really good for everyone. It's better for the framework author who doesn't want to maintain old versions of a framework. They want to be able to innovate and move forward and not be burdened by the decisions that they made previously. It's definitely good for the end consumer, because one change in a common framework has an impact surface area that is every application that uses that component. It could be hundreds or thousands of applications in the end, depending on how popular the framework is. So it's key, I think, that if the industry is to evolve continuous software modernization, that the refactoring tools that we use are open. And that's why OpenRewrite really is Apache license. Every recipe that I write, that people around me write, are Apache licensed, to kind of seed this new discipline with a set of valuable transformations that can get this thing going. Getting into the details of actual recipe writing would be a very involved topic, and we've got a short amount of time, but I do want to give you a sense of what it means to write a recipe. So let's look at one called avoid box Boolean expressions, which is a basic static analysis type thing. In the Java language, a capital B Boolean can be nullable, and when it's used and it's auto-boxed to a primitive in certain kinds of expressions, a null Boolean will throw a null pointer exception, the $1 million mistake. So it's better in those cases where B, like in this case, can be null, to wrap it with boolean.true.equals B, which is null safe. It's just a basic thing. But again, this feels like something that's difficult to do with a regular expression. I would have to identify usages of B, or things like B. Of course, B could be a variable, it could be a method, it could be a chain of method calls that they could span multiple lines, so it gets very, very hairy very quickly. But let's look at this recipe. The key I want you to kind of walk away with here is that recipes themselves are programs. Recipes extend recipe. They use the visitor pattern, and the visitor pattern allows us to effectively, with like an event-driven mechanism, respond to certain types of the parts of the AST. In this case, we want to look at expressions. We want to determine whether that expression is of type Java lang Boolean, and if certain other conditions are met, it's a control expression. We use things like templating to build up new little AST subtrees and insert them into the existing AST as a replacement for what's there already. The, I think, important thing about it being a program is that it gives us the full expressive power of the programming language itself to make the kind of change that we want to make. When we were looking at the JUnit 4 to 5 recipe, you saw that some of those sub-recipes were just building blocks, reorder method arguments, change type, add and remove dependency, and we get a lot of lift off of those base building blocks. But there were also quite a few recipes that were themselves programs that had some special logic. A good example was that one we saw earlier where you used to be able to define an exception on the annotation, but now you have to use assert throws. That definitely winds up being a recipe that's in its own self-contained class that handles that kind of change. And so it's really when you can do both that we're able to do these sort of big changes. I think when you build, so rewrite has an imperative base to it. That's where I would start. It's really just a program, and on top of an imperative base, we can always build declarative type syntaxes. We have a YAML syntax in rewrite where you can list recipes, base building block recipes, to construct a more complex transformation. But those are always shortcuts that help in addition to that imperative base. One of the common questions we get is about the language support that OpenRewrite has. And it started in the JVM. After all, it started at Netflix, which is a heavy Java shop and still is to this day. And so the strongest complex language support is in the JVM. In the last couple of years, we've been expanding the framework to other languages, especially infrastructure as code. So YAML, properties, XML, JSON, HCL for Terraform, these sort of things. That's allowed us to test some of the generalizations of the framework that they'll work well across multiple languages. And an interesting discovery we made earlier this year is that there's also what we call grammar islands of self-similar languages, such that for example, Groovy and Kotlin both extend from the Java AST. They're really, even though they can look very different in text, at the AST level, they're basically the same, such that a recipe that we've written like JUnit 4 to 5 for Java automatically works on Kotlin and Groovy. That's a very surprising result, I think. Interestingly, Python, TypeScript, and .NET are also on that same grammar island with Java. And so some of the base building block recipes we've written, like change method name, import manipulation, these sort of things, will automatically work on those new languages as they come online. And in terms of timeline, Python, TypeScript, and .NET are scheduled for arrival by Q2 of 2023. So expect those, more interesting, framework migrations like Python 2 to 3, React and Angular updates, these sort of things to be coming online by mid next year. And always happy to take contributions and collaborate with others in the development of those language ecosystems as well. It's been a joy to be able to introduce this to you today, and look forward to the live discussion.